Hello everybody. In the last class, we discussed about the three-phase circuits. We continued our discussion of the three-phase circuits and progressed naturally into the discussion of three-phase transformers. And the three-phase transformers, basically it is very similar to what we discussed in the three-phase circuits. You have 3 coils on the primary side and 3 coils on the secondary side. We connected the primary set of coils and the secondary set of coils in different topologies. So, as there are 2 main categories of three-phase connections, that is the star and the delta, we connected the primaries and the secondary in these various combinations. That is, you have the delta connection, that is the primary side delta, secondary side delta. You have the delta star connection, the star delta connection and the star star connection. So, these 4 configurations we studied, had a look at the various relationships between the phase circuits and the line side parameters of the primary and the secondary side, and we also were able to study the phasor diagram for these 4 types of 3-phase transformers. And then we summarized towards the end of the last session, we summarized the different types of the 4 different types of 3-phase transformers, as I am showing it here on the page. The relationship between the line voltage and the line currents. So, you see that in the delta connection, the terminal voltage on the secondary side is just by a factor of n times the primary terminal voltage. And in the case of star delta, the secondary terminal voltage is also multiplied by root 3, and in the case of the star delta, the secondary terminal voltage is divided by root 3, and the star star also you have a terminal relationship of with a factor of n. Note that with respect to the delta and the star star here, if we have, let us say, in both cases a given voltage, in that case the windings of the transformer here will have to withstand a higher voltage, because let us say you have a 400 volt system and the windings of the primary side should withstand 400 volts and the windings of the secondary side should withstand n times 400 volts, because in the delta connection the windings come directly across the terminals or the line. In the case of the star, the windings are phase quantities. The voltage of the windings are 1 by root 3 times the voltage that are coming across the terminals. So, the windings will have to withstand whatever quantity on the primary or the secondary by root 3 times. So, it should only withstand 1 by root 3 times EL and 1 by root 3 times NEL in the case of the star star connection. Of course, for the same power, the currents on the line currents will be the same, but the phase currents in the case of the star will be higher compared to the delta. So, that is where the compensation. So, in the case of the delta for the same power and voltage ratings, this is supposed to have a higher core cross section area in the case of the delta to withstand a higher voltage, but the gauges of the wire will be thinner, and in the case of the star it can withstand a lesser voltage, but the gauges of the wires will be thicker. Anyway, depending upon the application, the relationship between the voltage and the currents, the one of the 4 types of configurations or topologies can be chosen. There is one more interesting configuration which will have application in some of the circuits, and that is a transformer which takes as inputs the 3 phases A, B, C, where the voltages of the 3 phases are displaced 120 degrees apart, all having equal amplitudes, effective amplitudes, and the outputs will be 2 phases. I will call this one as alpha and beta. So, what this transformer does is a 3 phase to 2 phase conversion. Now, if you look at the practical application of this, one may wonder what where it can be applied. Of course, in some of the motors are 2 phase motors, or in the case of some applications where you have a 3 phase mains available, but the motor is a single phase motor. A single phase motor can be designed such that you do not need that capacitor, because some of the single phase motors need the capacitor to produce a rotating field, which we will discuss much later. The 2 windings of the 2 phase transformer can be used for such an application of rotating a 3 phase a single phase motor. There may also be few other applications where the 3 phase to 2 phase conversion can be used, and that probably would be in sensing a 3 phase signal like a current or the voltage, and then converting it to 2 phase coordinates, which will give a resultant, especially in applications like vector control or 3 phase control and those kind of applications where you need to convert from a 3 phase to a 2 phase system, and this could be a sensing transformer which could do that job. Anyway, there are few applications for these. Now, how does this come about? There are 2 methods. There may be more methods, but anyway I will explain to you 2 methods. One is using a single phase transformer. Single phase transformer, but we will use just one single phase transformer. In the other method, it is called the Scott or the T topology, where 2 single phase transformers are used. 2 single phase transformers are required. Let us have a brief discussion on these 2 topologies before going on to the next topic, because they are interesting, and then it can have some interesting and ingenious applications. So, let us start with the fact that 3 phases are available to us, lines A, B and C. These are available to us, and let us make the following connection. And I have a single phase transformer which is the primary. I am going to take the primary, and to the primary terminals let us make the connection, the A phase connection here, the B phase connection here, and the C phase connection is C line just goes out like that, without getting connected to any part of the transformer. Now, let us take the midpoint of this transformer and take that out. Okay. Of course, now the polarities. There is a dot here. Now, the secondary of the transformer is the other phase that we take out. Or equivalently, let us first discuss with just this primary coil with respect to the dot, so that we understand the various phasors. Now, let us, this of course is A, this is B, this is A, this is B, and this point we will call it as M. Okay. Let me make a dot here, and this is C. Now, let us draw the vector diagram, phasor diagram. Now, we know that ABCs are as follows. So, if I am having EAB along this, EBC will be 120 degrees lagging EAB, and then you have ECA another 120 degrees lagging EBC, or 240 degrees lagging EAB. This is now what is the potential EAM? So, this is EAB. Now, what is EAM? As it is at the midpoint of the winding, EAM will be half of EAB, and this is EAM. Now, what is the potential here? Now, this is EMC. EMC is equal to EAC minus EAM will be EMC. Now, EAC is actually the reverse of this. So, it is actually the reverse of this, which is EAC or minus ECA, and this EAC minus EAM will be so EAC minus EAM will be EMC. This is EMC. C, or EAM plus EMC is going to be EAC, okay, as you look at the diagram. Basically, the Kirchhoff's voltage law in this loop. So, if we see here EMC, the value of EMC, now if we take that this is unit wise, if this is 1 unit, this is 1 unit vector, this is 1 unit phasor, this will be 0.5 unit phasor, this is also 1 in amplitude. So, this is going to be square root of 1 square minus 0.5 square, which is equal to root 3 by 2. So, this will be 0.86 units. Now, see that EMC and EAB are 90 degrees with respect to each other. They are 90 degrees with respect to each other, which means they are orthogonal with respect to each other. So, EMC and EAB together can form a two-phase system if their amplitudes are equal. Now, EAB is having an amplitude of 1, EMC is having an amplitude of 0.86. So, let us take tap from here, let us 0.86 with respect to the winding here, and if we take E and let us say this is the tap point, okay, and this EAT. So, our EAT will be 0.86 amplitude. So, EAT and EMC will form an orthogonal set, that is, you will have EAT and we have here EMC. So, instead of using a tapped winding, we could use the secondary of the single phase transformer with a suitable turns ratio of 1:0.86. Then one could then use, under such conditions, one could use the secondary of the transformer with 1:0.86 as the turns ratio. Then the dot polarity as shown here, this will give EAT and EMC. This would be a 3-phase to 2-phase system. So, this system what is being shown here is a 3-phase to 2-phase transformer. Now, let us look at the second method, which is the Scott connection. This also is similar. We have two transformers. Let us say there is one transformer which is connected like that with its secondary like this. Then there is another transformer the primary is like that, the secondary is like that. So, we have this point is A, this point is B, this point is C. With the following dot polarities, we have the dot here and the dot here and dot here. We have a three-phase system A, B, C, where A is connected here, B is connected here, and C is connected here. So, this looks like a T, therefore, this is also called a T connection. Now, this is the center tap and we will call this as position M. Now, if we take the vector diagram EAB again, so I have EAB, EBC, is ECA. This is what you get from the supply, which is the source. Now, EAB, EAM are in phase because these are the same winding. So, EAM, and it is at the midpoint, and therefore, we will say this is EAM. Then ECM. So, what is ECM? ECM is ECA. So, this is ECA and this is EAM, that is EAM, and this is ECM. So, this is EAM, this is ECA, this is ECM. This is ECM. Now, let us ECM and EMA, that is EMA is the reverse of this, plus ECM should be is equal to ECA. Now, EMA is nothing but minus of this. This is EMA and this is ECM. Are you getting it? ECA equals, look at the Kirchhoff voltage law along these marked things, ECM minus EAM. Look at the arrow direction. This is equal to ECM plus EMA. So, this is what the two vectors which are combined. EMA is nothing but negative of EAM, just put in 180 directions, then plus ECM should add up to ECA. Now, this is having unit 1, this is having unit 0.5, and therefore, this has a unit amplitude of 0.86 or root 3 by 2. Or other words, you can say that this angle is 30, therefore, cos of 30 is 0.86 or root 3 by 2. So, what you get here ECM is 0.86 the amplitude of the. So, if we have, let us say, a ratio of 0.86 is to 1, then this will get amplified and you will get here you will get here, let us say, E beta and here you will get E alpha. So, E alpha is nothing but EAB, and we could have, let us say, 1:1 turns ratio. Now, this gets stepped up from 0.86 to 1 and you have E beta. So, we have E alpha along EAB and then we have E beta along this direction. This is the 0 and it is 90 degrees with respect to each other. They are orthogonal. You see that ECM is E beta, ECM is E beta, EAB is E alpha. So, EAB and ECM are 90 degrees with respect to each other, phase shifted, and therefore, they can form a two-phase system. Only thing is their amplitude is EAB has a unit amplitude, normalized amplitude of 1 and ECM has normalized amplitude of 0.86. Therefore, by adjusting the turns ratio of this transformer, the beta side transformer, with the turns ratio of 0.86 to 1, one can equalize the two-phase output. So, this is another two-phase transformer. This is called the Scott connection. So, till now we have been discussing about the three-phase transformers and the various parameters in it and how they are related, but functionally they are very similar, in fact exactly similar to the single phase transformer. It uses the same principle, that is the Faraday's law of electromagnetism, which is the induced voltage is equal to N times d phi by dt, that is the flux which is there in the core. It is composed of three independent, separate single phase transformers connected in various topologies. These three single transformers are then combined into a single core. The next transition from this three-phase transformers would be into three-phase machines. And this three-phase machines, the induction machine or the induction motor is very similar to three-phase transformer, except now the power or the energy is coming from the electrical domain and going into the mechanical domain. It also goes into the electrical domain, like in a three-phase transformer, electrical domain to magnetic domain to electrical domain. In the induction motor, you can have electrical domain to magnetic domain, to electrical domain, and also to mechanical domain. So, we have a system, a central cauldron or the drum, which we say is the magnetic domain. So, to this magnetic domain there is an energy input. So, this is the energy input, and in the case of the transformer there was an energy output. This is an energy output. So, the transformer is a two port system. There is an input energy and the output energy, and this is in the electrical domain. This is in the electrical domain, and this also is in the electric domain, the output. Now, this would be the structure of a transformer. Now, if we had one more output apart from the electrical output, we have energy output in the mechanical domain. In the mechanical domain. So, this is the basis for the induction motor. Induction motor is like a three-phase transformer, where it takes energy from the electrical domain and then puts it to the mechanical domain. There is also a class of induction motor where part of the energy can also go into the electrical domain, like in a regular three-phase transformer, and part of it can go into the mechanical domain. So, let us study the induction motor, which is probably the most ubiquitous motor that you would find in most of the applications all over the world. Something like 75 to 80% of the prime movers are induction motors. The everyday pumps that you use for pumping water from the sump to the overhead tank, they are induction motors, work on the induction principle. The motors that are used for the cranes, induction motors. The motors that are used for the fans, the blowers, they are all induction motors. Today, the induction motors are also used for precision mechanics, for spindle drives and speed controlled drives, and also in feed drives which require very great precision. They are all induction motors. So, majority of the prime movers that you see are induction motors. So, it is essential that we know something about this very popular motor, which is used in the industry and everyday applications. Now, induction motors come into varieties, two major varieties. One is called the squirrel cage induction motor. The other is called the wound rotor induction motor, or slip ring motor. So, as the name suggests here, in this case the energy enters from the electric domain and goes to the mechanical domain. And in this case, there is a possibility for the energy entering from the electrical domain to be tapped either to the electrical domain or through the mechanical domain. So, by means of slip rings that we discussed while we were discussing the DC generator, the principle is precisely the same. So, what makes the induction motor move? Before we look at the structure, we should understand the basic principle of the motion of the induction motor. You see that the induction motor is composed of the shaft, which is the rotating part of the induction motor, and that is called the rotor. And then there is another part which is fixed and stationary, and that is called the stator. Now, the rotor has on it the conductors. All around the circumference of the rotor you have conductors. The conductors in the case of the squirrel cage induction motor are shorted at both ends, such that the rotor looks like a squirrel cage. So, that is why the name the squirrel cage induction motor. And the case of the wound rotor, these rotor coils are brought out through slip rings and brushes, like in the case of the DC machine, but through slip rings, not commutator, mind you. So, which means the current in the external electric circuit is also AC. So, you have these rotor conductors, and then on the stator also we have coils, but the coils are positioned in a manner which will provide field, spatial field in the spatial coordinates. So, let us see how that is provided, and that is basically done by having some coils here, let us say. So, let us say we have some construction here, and you can have a coil here, and this coil goes around and connects to this pole, then comes out. Okay. So, like that there are many poles around which the stator coils are wound, and we have the field which is getting generated. Now, let us look at a segment. Let us look at a segment of this induction motor here. So, you see that we have let us have some conductors of the rotor, these are conductors of the rotor, and of course, these conductors go back this way. And so on. So, we have the conductors which are mounted on the rotor in this fashion. And let us say there is current through the rotors. That is, we have current flowing through the rotors, and also let us say that there is a field of density B. So, we have a field flux of density B, and there is a motion, that is these conductors are rotating, and these conductors have a length L. So, if you recall the Lorentz force, we have the field B, then we have a current I which is flowing through the conductors. There is a current I which is flowing through the conductors, and this is going to provide a force, and that force is B I L. B I L. This is called the Lorentz force. Now, what causes the current in the conductors? And that is by the Faraday's law. See that there is a force. By Faraday's law, there is a voltage E induced, and that is given by B L V, where V is the velocity of the conductor, velocity with which the conductor moves relative to this field, or the relative velocity, we will call it the relative velocity between the field, that is B, and conductors and the conductors. So, there are two ways in which to bring about the relative velocity. You can keep the field fixed, as we did in the case of the DC machine, and the conductors were moved, or you can make the field rotate and the conductor also moves and tries to catch up with the field. So, you have these two effects which come into play in the case of the induction machine. So, first of all, how do we make the conductors rotate, or how do we create this relative velocity? Because that is what is going to induce a voltage on the rotor conductors, and that is going to create a I, and therefore, B I L. There will be a torque on the conductor which will make it move. So, this would be the Lorentz force, and this is the Faraday law. So, the main question is, how do we bring about this relative speed between the vertical, the green B phasor or the B field and the conductors which are orthogonal to each other, or how do we make the B cut the conductors. So, in the case of the induction machine, because we have a three-phase system, it is possible to generate a B phasor which is rotating in space. It rotates in space, and that is called the rotating magnetic field. Rotating magnetic field. So, how do we generate this rotating magnetic field? The rotating magnetic field is generated by a combination of constraints that are applied. One is, we need to have, let us say, a three-phase or two-phase system supplying the voltage or current. Now, let us take for example for now just three-phase system. So, in the case of three-phase system, we have VA, VB, VC, or we will say EA, EB, EC, and then you have IA, IB and IC. These are the three, this is a knot, this is the three line voltages and the line currents. Now, all are having the same magnitude and displays 120 degrees apart, and this displacement 120 degrees apart is in the time axis. Now, these are displaced 120 degrees apart along time axis, which means the displacement between the IA, IB, BC 120 degrees apart is along the time axis, which when we talk of as phasors in the spatial coordinates, it reflects as 120 degrees three phasors. Now, let us make one more condition, the second condition. There should be three field coils on the machine. There should be three field coils on the machine which are placed 120 degrees apart in space. So, this is the second condition that is needed to generate a rotating magnetic field. Let us see how that comes about. So, let us say we have, let us say we have a pole which is like that, and the other end of the pole which is like that. Now, let us say if this is the north pole and this is the south pole, we are having a field direction which is like that, north to south. So, this means that we have some windings on this and let the current flow in this direction, which will give a field in this direction, and we should have also a coil wound here with the current flows in this direction, such that we have the field. So, these two will aid and we have a field in this direction. Now, we want to have the same current to flow through both, that is a current, let us say I, which flows through this coil, and let us link this coil to this, and this is brought out and then given to a source. So, now this source sees a inductive reactance because of the coil, and this is going to pump a current in this direction as shown. It comes in this fashion, sorry, a slight error in the connection here. So, the current flows in this direction, then gets connected here, flows through the coil in this direction, and then comes out here. Yeah. So, we have now a field this direction. Now, this pole is physically located in space, and let us say this is the plane, this is the plane, this is the reference axis, let us say this is the spatial reference. Then we say that this pole with an axis like that is 90 degrees located 90 degrees with respect to the reference. Likewise, let us say similarly I have a pole which is located in the following fashion. So, let me have one pole which is one set of pole which is located like that, as shown here. So, let me call this as one axis. Let us say this is the horizontal axis. This pole set is at 0 degrees with respect to the reference axis. So, this is the reference axis in space. Okay, this is spatial. Then let us have another pole set which is 120 degrees displaced with respect to So, let me have one more set of pole which is like that, and one more which is 120 degrees displaced, which is of this nature. So, we are going to say that these two are one pole sets, this is one pole set and this is another pole set. So, this pole set is fixed in space, this is not rotating, this is fixed in space with respect to the other. So, let us say that this green one is the A pole set, the red one is the B pole set, and the blue one is the C pole set. So, if you see the if I mark the a polarity in terms of dot or the north, let us say these are the norths, this is the north and this is the north. Okay. Then we have some dot polarity, let us say it could be any similar phase, but this is the positive side, and we have for the A and then we have for the B. So, the A pole set axis is going to have the flux in this direction alone always, there is no other movement. The B pole axis, the C pole axis is going to cause a field only along this axis, and the amplitudes here can be varied depending upon the currents that are going to be passed through the C coil, and the B pole axis will have the field only in this direction, and the currents through the B axis, B poles are going to modulate the amplitudes of the flux here. Now, by fixing these poles in space, fixed, and now these are 120 degrees with respect to each other, this is 120 degrees and this is 240 degrees. Now, they are 120 degrees with respect to each other in space, they are fixed firmly, and then the flux densities in each of these axes are going to swing only in those axes, and they can be modulated only along those axes by controlling the currents through that axis. Now, if we apply, let us say, the A phase current to the A pole set, the B phase current to the B pole set, C phase current to the C pole set, you will see that the resultant flux density will rotate with the frequency at which the currents are provided for the pole axis, pole coils. So, we will see how we generate this rotating flux with the means of the three phase currents IA, IB, IC passed through this stationary pole axis as shown here to generate a rotating flux. We shall discuss this further in the next